Hey, hi there. In today's video, we'll be exploring the first part of hypothesis testing, right? So in this video, we'll be looking at the z-test and the t-test. Typically the test which we were using for confidence distributions in the beginning, right? So z-test and z-test and t-test. So let's first use z-test to understand how we implement z-test in Python. And we'll do that by using a real life data set and import it as a CSV file in the form of a CSV file. So let's first import all the necessary libraries. So for probability distributions, right, when we wanted to calculate the probability with respect to some particular value of, statistic, particular value of random variable, we imported the library, which is scipy. For hypothesis testing also, we'll be using the same library, okay? Import scipy.stats as stats. Once we import this library, let's read the data set first. So data set is inside the folder, which is data sets, right? And then, so this is the wine data set, okay, which basically contains the points, or what we call as the score given by individual wine tasters to different wines, okay? And the question is a sample of wine scores from the wine enthusiast population. Okay, let's try to understand the problem statement. Let's assume that the wine enthusiast point scores are interval scaled normally distributed data. So let's assume that it's a normally distributed data. Let's find the population mean and population standard deviation. So basically what I'm trying to say here is the entire data, the Excel sheet, in the Excel sheet is considered as a population in this case, because we'll be extracting a sample from it and then compare with the mean population. Okay, because we do not, in this case, we do not have prior knowledge of the population standard deviation. We use z-test when we have the population standard deviation. When we do not have the population standard deviation, that is when we use t-test, right? So we are bound to, consider the entire, CSV file as the population in this case. So whether you treat it as a sample or population depends on the problem statement which you are solving. What is the question at hand which you are trying to solve? So here, a sample of n equal to 10 samples, point scores, yields a sample mean of, let's say sample mean of x bar is equal to 90.2. So this is given to you. Let's say we have extracted a particular sample from this entire column, and whose sample mean was found out to be 90.2. Okay, we'll also do all these hypothesis tests on as case studies in the upcoming videos, guys. Okay, so here I've defined it for you so that we don't have to go there and pick up samples, but I'll show you how to randomly pick up samples and then compare the means as well in the case studies. But for now, let's continue with the problem statement and try to first start, understanding the concepts from scratch. Is this sample from the wine enthusiast population or not? So basically what I'm trying to say is this X bar, is it equivalent to the population mean? As simple as that. To answer this question, we'll use a z-test, one sample z-test, okay? And of course, we will not use any Z table here. We'll be directly using inbuilt functions to calculate the probabilities, whatever it is required, p-values, z-critical, whatever it is required. So we have two ways of inferring from hypothesis testing, right? Whether the null hypothesis should be accepted or rejected. One way is by comparing the z-stat, the calculated z-stat with the z-critical value. This z-critical value is typically calculated from the Z table. And here we will not do that. We'll be using a different function to calculate it. There's the other way is by comparing the p-value with the alpha. Now, alpha is something which we already assumed, typically 5%, right? P-value and z-stat is directly calculated using a single function in statistics in the scipy module. So we don't even need to calculate the z-critical if you think about it, because once we calculate the p-value, I can directly compare with the assumed alpha value, right? So we do not need multiple steps here. So let's do that. So first, let's import the necessary function which is required. So from stats model.stats. So here, instead of from scipy.stats, we are importing it from stats models. Okay, from stats model.stats, import weight stats. From weight stats, we'll be actually importing the z-test. Okay. Okay. So alpha is equal to 0.05, which I've already assumed. Sample mean is given to us 90.2. X is nothing but the entire date, column of points, scores, and my mu will be nothing but X dot mean. Okay, and sigma will be the population standard deviation, because we have already considered the entire column as population, so it's X dot std. Okay, mu and sigma. Okay, so now first step would be to extract the Z statistic, calculate the Z statistic and p-value, right? Calculate Z statistic and p-value. And that can be done simply by using a function which is called as weight stat dot z test or z test. Now these hypothesis tests, all these hypothesis tests which you have in Python typically gives you two values, the statistic value and the p-value. Okay, and it gives the p-value for a two-tailed test, or two-sided test. Okay, so z test, what does this function require? This function basically requires three arguments. One is x1, x2, and the value. Value means it requires the sample mean. Okay, here in fact we do not need x2 here, because x2 by default is none. None means it's a one sample z test. So let's look at the documentation once. Okay, so if we go here, so x2 is none by default, so I don't need to again express it here. I can simply, for one sample z test, I can simply put the array which I would need, which is nothing but x1. So this is x1 actually, and the value is nothing but the sample mean which I need. Okay, so once I have that, I get the Z stat as -207, which is very, very, very towards the end, right? So obviously here, my p-value will be very, very less than alpha. See, it's 0.0. So what does it basically mean? If you want to visualize this, it will look something like this. 0, Z is mean is 0, -207 is extreme, and this is where my p-value is lying, right? Correct? This is my p-value, whereas my alpha is much bigger, right? 0.055%. This is much smaller. It's almost zero, negligible, right? So it's falling in the rejection region. So my null hypothesis will be rejected. So what will be the the alternate hypothesis? That it is not from the same population. Okay. Sample was drawn from some different population other than the population which we have in the form of an Excel sheet, right? Now, if we change the sample mean, okay, if we change the sample mean to say 88, okay, 88.45. Earlier it was 90.2, now it is 88.45. What happens? You can see here that the p-value suddenly increased, right? The p-value has suddenly increased. In this case, it means that we are accepting the null hypothesis rather. Okay, so here Z stat and Z critical value. So here we're not going to find a Z critical value anyways. We'll just compare P with alpha. So if P is less than alpha, we reject the null hypothesis, of course. Otherwise, we accept the null hypothesis. So in this case, we'll accept it. Now, why? Because my sample mean 88.42, right, is the sample mean. What about my population mean, right? Let's say my population mean was this dot mean, right? This was a population mean, and you can see here, as the sample mean is closer to the population mean, we can say that my sample actually belongs to the population, right? Okay, so that is why it was matching, right? The mean was very close, sample mean and the population was close to each other. That's why you can say that the sample belongs to the population, right? So here also you can see here mu, right? So it's already given mu. So we can call this as mu, right? Now let us try to try out some more, try some more values, right? Let's say if I make it 88.45, 88.5, let's see. If I make it 88.5, still it is rejected. See, this p-value is much less although not as less as the first case, but much less than this, right? So it's very, very, sensitive. That's what I'm trying to say here. So now if you look at this, right? Earlier, my Z value was negative 206, which was very far away towards the extreme side, and hence the P value is very less. Then we have say 88.5. When a mean value, sample mean is 88.5, my P value is minus 0.6. So it may be somewhere here. Slightly the P value increased. And then if it is 88.45, which is here, the P value will further increase. In fact, it crossed the alpha value, which is 0.05, right? Okay. So which basically means that the dataset is very sensitive, right? And for it to be for the null hypothesis to be accepted, right, it took the sample mean to be 88.45, which is very, very close to the mu, which is the population mean. So this is how you can play around with different sample means and check, what is the difference between the sample mean and the population mean, for which we can say that the sample belongs to the population, right? Okay, so even in this case, the null hypothesis will be rejected, right? Here it will be accepted. So we can statistically say that sample was drawn from the one enthusiast population. So in order to sum up, if I can just explain few simple words, my mu is 88 point, how much is the mu? 447, right? 88.447. And my X bar, which I had tested before, was 90.2. Then X bar, let's say 88.5. Then X bar, say 88.45. Okay. In this case, my P value was very, very small. It was almost 0. Okay. Here it was again very, very less, 3 point into 10 to the power minus 10 or something like that, right? 1 to 10 to the power minus 10, whatever it is. Okay. And 10 to the power minus 10, correct. And then we had this where it was 0.73. So you can see as the difference between the mean, population mean and the sample mean closes, narrows down, my P value increases, which means the probability of my null hypothesis getting accepted increases. So in both this case, it was rejected. The last case, it was accepted. Last case means in the middle case, which we have found out here, right? 88.45. Correct. So this is how you need to understand the influence or the impact the sample mean has on the P value. Okay. All right. So next we have t-test. Now let us look at some of the examples of t-test. Okay. So these are some theory which I have put it across for you so that you can read across and revise from what we have learned in the lecture series. So one sample location t-test will do on whether the mean of population is equal to the specified value in null hypothesis. Okay. The mass of a sample of n equal 20 acorns from a forest subjected to acid rain from a coal power plant are given below. So this is a mass of 20 acorns. Is the average mass of this sample different from the average mass of all acorns, which is given to you, which is the population mean 10 grams. So here you have to consider this entire data as sample data. Okay, definitely the hypothesis statements will be this, correct? Two-sided test hoga. Degree of freedom we all know. T critical we are not going to directly specify like this. We are going to calculate it. Okay, we are going to calculate it. Okay, so let's say x is equal to this. My mu is given as 10. My degree of freedom will be 1 minus length of x minus 1, n minus 1. We can address it. And my X bar is nothing but my NP dot mean of the X, which is sample, which is given to me already, right? So I've calculated what is required. Now to do t-test, again, we have to calculate the t-test, t-statistic and the p-value, two-sided p-value, right? Okay, just like we have in z-test. But for z-test, we imported, stats dot, weight stats dot something, right? Z-test, right? Here it will be stats dot t-test underscore 1sam. T-test underscore 1sam. This is from the scipy module. Okay, t-test underscore one sam. And this one sample t-test requires two parameters, the array of the sample array, sample data points, and the population. In Z, it was different, right? It's Z, it required the entire population data, comma, the sample mean. Here, it is a sample mean, comma, the population mean. Once we have this, I can easily calculate the t statistic and the p-value. Okay, I think X is from above, so I have to run this. Correct. So now I have minus 2.2, 0.03. So p-value is slightly lesser than the alpha value, which is 0.05. Right? So alpha I'll again assume it to be same thing. Alpha is 0.05. So we'll reject the null hypothesis, which means that this sample is different from the population. The sample mean is different from the population. The either way, the second method is to calculate the Z critical, the T critical, of course. Here it will be actually T critical, right? Because we're doing the T test. Okay. Now, how do I calculate the T critical for a two-tailed test? And that too, this P which we are getting actually is for two-sided, right? So we're directly getting the two-sided P value and comparing with the two-sided alpha value. If this would have been a one-sided test, I would have to divide this P value by 2, right? Because we'll be comparing on only one side. By default, Python gives you the P value for both the sides. So if for one-sided test, you have to cut off one P and compare with the alpha. It's practically reverse of what we do in the theoretical, in theory or in manually. Okay, in manually, we already have a table for one-sided separately. That's why we divide the alpha and then compare. But here, by default, it can only give you two-sided P value. So we'll have to divide the P and then compare with the alpha. So unlike the question which is given as the critical, you have already specified it, but actually we don't need it. We can simply calculate. I've specified it so I can compare with how we calculate it from in Python. Okay, so for that, we need something. Now, whenever we want to calculate the Z value, remember the probability distribution table, right? The probability distribution video which we had in code, right? Stats.norm.cdf gives me the probabilities, whereas stats.norm.ppf gave me the Z value. Similarly, here also we'll have stats.t.ppf, t-test, which means t-distribution, right? So see, stats.t.ppf. Very simple, guys, right? And one more thing which I want to mention here is that now, for what value, do we require, right? Okay, so ppf, if you remember, there we just had to put one value, right? The value of the probability 0.98, 0.95, whatever it is, right? And directly give us the Z value at that, the previous video which we saw. But here we are doing it for a sample, and that's for t-test, right? So we need two things here, degree of freedom and the probability as well, right? So degree of freedom will be n-1, very simple, whereas probability is something which I need to focus on now. So see, alpha is always on the extreme end, right? Correct. And it's a two-sided alpha here, correct? So for two-sided alpha, if I want to find out the T critical, I'll only find it from one side, right? So I have to divide it by alpha by 2, obviously. Okay. Now this region is alpha by 2. This region is alpha by 2. Okay. Now, if I want to find out this value, T critical, what will I do? If I have to use the PPF function, right? So the PPF function, if you really look into it, right, it takes in that probability, right, which is enclosed by the critical, by the value which we need to find out, right? So जो यहाँ पे पहले Z था, right? The Z, if I do 0.98, it means that, right? It means that this Z covers this much of area under the curve. So here we actually need TC, which will be covering not alpha by 2, but 1 minus alpha by 2 of the curve. And if I do this, whatever T value I get, that will be my critical value. Got it? So that is why I'm, instead of directly putting alpha value, it will be 1 minus alpha by 2. First of all, it's two-sided. That's why I'm doing alpha by 2, and it will be 1 minus, because I have to find out less than that particular area, right? From the left-hand side, I have to calculate. Whatever value of Z or T we calculate, it's always from the left hand side, right? So that is the trick. This is how you need to understand. Okay. So this is my critical value, see 2.09, which is matching with the one from the table, which was again 2.093. Once I have this, I can compare with t-stat. T-stat, we already get it from t-test underscore one sample. I can easily compare t-critical and get the same conclusion. One can argue saying if I'm already calculating t-stat and p-value using the same single function, I can directly calculate compare p-value with alpha value to get the conclusion. Why do I need to again calculate t-critical? I completely agree with it. But, if I show you how to calculate the t-critical also, your concept remains absolutely clear. Same thing which I was doing before, is just that, tweaking here and there, right? T-critical. Right? T-critical is that point beyond which lies the alpha value, right? So if I have to use the alpha value to find the critical value, I have to do 1 minus alpha, because that function of PPF will give you the value of the random variable, which encloses that amount of probability. That is why I'm doing 1 minus alpha by 2. Very simple, guys. Okay. So next, if I want to focus on the 95% confidence intervals, because it's 5% alpha, right? So confidence level will be 95%. So my SE is nothing but standard error, and standard error is actually given by sigma by root over n. Okay, in this case, it will be sample standard deviation. Okay, so sample standard deviation will be xtd ddOF equal to 1, because sample standard deviation, and by root over n, length of x to the power of 0.5. This is exactly what should be SE. Let's see, list has no attribute. Okay, my x is a list, is it? Okay, so let's make it x underscore standard deviation is equal to np dot standard deviation of x. Let's see if this works. Okay. T critical is already calculated here. T critical. Okay. Right. So that is already a sample. So I don't need to again use the sample formula. I can directly calculate the standard deviation directly, which I've done it before above. And this is my error. Okay. T critical into SE. Okay. So basically how it works is very simple. The what you call as the low and the high, right? Okay, the interval, right? Low interval and the high interval. So first we calculate the error term, which is T critical into SE. My SE is nothing but sample standard deviation divided by sigma by root over n. Okay, once I have this, right? Once I get this done, next what I'll do is I'll calculate the lower threshold, until given by x bar minus x bar mean, sample mean minus this error, and x high will be x bar plus error. That's it. Once I have this, so this is my x bar and this is my 95% confidence interval. Okay, within this interval, I'll be 95% confident that my hypothesis conclusion is correct. Very simple. We can also get the confidence intervals directly by using the inbuilt function of t dot interval. See? Stats dot t dot interval minus alpha, like this is degree of freedom, and this is location again is x bar, scale is equal to SC, which I've already calculated here. Okay. So and you can see here we get the same result, exact same result. So better to use this. Why to calculate all these things, right? Okay. This is nothing but degree of freedom. Okay. Great. So next is independent two sample location test with a null hypothesis that the means of the two samples are equal variance. Assume that is always the case. Whenever we compare two samples in t-test, we assume that the population variance are the same for both the samples. So the mass of N1 equal to 20 N2 equal to 30 acrons. So we have two samples now from oak trees upwind and from oak trees downwind. Okay, the masses are recorded and the masses are these which are given. Okay, sample upwind, sample downwind. So basically we have to find out if there's a difference in the sample means or not. Whatever, if we do not, so the sample sizes are not equal, but we'll assume that the population variance of sample 1 and sample 2 are equal. Okay, this is fine. Now, what is the question now? Are the acorns from trees downwind less massive than the ones upwind? Less massive than the ones upwind. So upwind is x1, downwind is x2. So they're asking x2 is less than x1. That would be in the alternate hypothesis. So this is a one-tail test, guys. This will be a one-tail test, not a two-tail test, because whatever question is being asked typically falls in the alternate hypothesis, and the more complex statement always forms the alternate hypothesis. They're asking if x2 is less massive than x1, right? So this is what it is, a one-tailed test. Okay, so for two independent samples, we should use the inbuilt function stats.independent. And why independent? Because these two samples are independent of each other. The formation of one sample is not dependent on the formation of the other sample. So we'll use test underscore independent, IND. It requires two parameters by default, x2, x1. Okay. And equal variance equal true is the default parameter, which is already there by default. So we do not need to use it, right? So I can in fact remove this out as well. Okay. So let's calculate the stats dot test underscore independent x2, x1. It's already given down and upwind. And here it's a one-sided test. So whatever p I get, it's actually two-sided. So I have to convert it to one-sided by dividing it by 2 and then compare with the alpha. So x2 is not defined because I have not run this, right? Great. So once I get all this, I can compare it with the one-sided value, p one-sided. We get the null hypothesis because my p one-sided is actually 0.03, which is of course less than the alpha, which means that it is lying on the rejection region. My null hypothesis will be rejected. In fact, here I can remove all this because we don't need two-sided actually here. Here are the hypothesis statements I've already mentioned here in the question itself. Okay. Next, we have paired sample t-test. Now, paired sample means both the samples are somewhat, one of the samples is at least dependent on the other sample. You can see here the average mass of acorns from the same N equal to 30 downwind, which was x2, is measured before and after. So now x1, x2 is different. This x1 is not from upwind. This x1 is from downwind, but it's before and after the power plant converts from burning coal to natural gas. So before the conversion of coal to natural gas, before the conversion, it was x1. After the conversion, it became x2. Right? From the same downwind, which was x2 in the previous question. Okay. So this is what it is. Right? Does the mass of acorns increase after the conversion from coal to natural gas? After, right? Mass of acorns increase after. So x2 greater than x1 is what is being asked in our alternate hypothesis. Very simple, guys. To avoid confusion, what I'll do here, I'll just simply, instead of making it 1, I'll just simply do before okay. So once we have, so I've changed the x1, x2 to xb and xa. Xb means x before, xa means x after. So it becomes convenient for you to, understand the question properly. So here, before conversion, so xb, after conversion, say xa. Okay. Next, what we'll do here, instead of using stats.test underscore independent, we'll use test underscore rel. So rel means it's a paired t-test. Okay, and I'll use before and after. So once we have this, this p-value is of course much less than the one-sided p, correct? One-sided will be, so this p-value, which is one-sided actually, is less than the alpha, which is 0.05, of course. That's why we'll reject the null hypothesis again. So there's a statistical difference between two samples at alpha is equal to 0.05. So after the conversion from coal to natural gas, the mass indeed is very, very different. Okay, in fact, it is greater than the one which we had before. Okay, and you can actually test this as well, right? Okay, so if I have x a, right, xa, which is after dot mean, okay, it's a list, so I have to use np dot mean of xa is this, whereas np dot mean of xb is 9.6. You can see here xa is significantly, it is more than xb, but to hypothetically understand, quantify this difference, whether it is significant or not, we had to do the hypothesis test. So this 10.1 minus 9.6, whatever it is actually significantly different at alpha is equal to 0.05 level. So I've noted down some functions here for you to remember so that you don't forget whatever functions we have used so far, just to sum it up. Now, let us pick up the question which we had from the slide, right? A study was done to see the effect of presence of dogs, of pets on kids. And we have two samples of people or students, one with dogs and one with no dogs. We have to see whether dogs have a significant effect on the cheerfulness of kids, whether it's positive or negative. So the alternate hypothesis will say mean cheerfulness of dog, people with dogs, not equal to mean cheerfulness of people with no dogs. Very simple. This is something which we have already covered. But I just want to show you how we apply the same question, solve the same question using Python. So here XD means sample with dogs, array of this, sample with no dogs, which is already given the question. Next, we have to calculate, since it's a two-sided test, we directly calculate the p-value, p2-sided, from stats.t-test underscore independent. We have two samples here, and both these samples are not dependent or paired with each other, right? Unlike just the previous example which we have done. So we directly put in x1, x2, dog and no dog, and then calculate the t-stat in the p2-sided. So let's say print, let me print it out as well, print t-stat and p-value. So this is my p-value, this is my t-stat. And if I want to compare with alpha, this is again alpha. And alpha is typically assumed to be 0.05. So here we'll accept the null hypothesis, the same result which we had got in the slide as well, because the p-value is, two-sided value is pretty high, much higher than this one. So here you can see the p-value directly getting calculated as 0.509, and the t-stat has been calculated as 0.67, same value which we had got in the calculation which we had from the slide. In the video where I was explaining the theoretical part, probably these values were slightly different because I made some calculation mistake. These are the defined, the new values or the rectified values, and the PDF of this slide which I'll be uploading will have the corrected values. Okay. It doesn't change the hypothesis conclusion because this is still less than a critical value, but this should be 0.68. Earlier, I think it was 0.35, which I explained in the previous video. So this should be 0.68, this should be 0.92, and this should be 7.48. Okay, so you can see here, this is 0.68 after calculation, this is 0.67, almost same, right? And of course, it's less than the critical value. But here we have not calculated the critical value. We're trying to compare the p-value with the alpha. So p-value is pretty big, more than 10 times more than alpha value, right? So of course, we'll accept the null hypothesis. Now, if I want to calculate the t-critical and compare t-stat, what will I do? For t-critical, what do we have, right? So for t-critical, correct, as we had done before, t-test dot ppf, right? stats.t.ppf of the probability, which is 1 minus alpha by 2, because it's a two-sided test, comma, we also need to put in the degree of freedom in this case. The degree of freedom is 16, right? From here as well, right? So once we get it, This is the T critical, which is 2.119, just same as here, right? And then we calculate the, we compare it with the T stat. Since here's T stat is less than T critical, we'll again accept the null hypothesis. So whatever way you use, either we compare the P value with the alpha or the statistic value with the critical value, we'll get the same conclusion. So in this case, null hypothesis is accepted, which means that there is no significant difference in cheerfulness when a person has a dog, right? So dogs do not have any effect. One more thing which I wanted to tell you guys before we end the session today is the degree of freedom. When we calculate for t-test, typically we choose the sample with less number of elements and then subtract 1 from that particular length of the sample. Okay, so in this case, both of them have the same length. So we can use simply un minus 1 will be 16. That is what we are explaining in the slide as well, right? So typically we take the smaller of the samples and then subtract 1 from the number of elements in the smaller sample. Please not forget that. So I guess that's all for today, guys. I hope you guys are learning and that these videos are adding value to your knowledge. This is how we implement t-test and z-test in Python. Okay, we'll have respective case studies also in the upcoming videos. Whatever we have done in the slide, we have validated them using Python. So you can easily understand how easy it is to implement those hypothesis tests in Python rather than doing it manually. So whenever we have a huge number of data set, right, it's not possible to do it manually. So we can directly use this function to get our conclusions. Okay. So guys, stay tuned. Looking forward to seeing you in the next video. So in the next video, we'll be covering chi-square test, which is a different test from z-test and t-test. Those tests are typically used for category variables. First, we'll cover the theoretical part of it, and then followed by the application part, which we'll do using Python. Hope you've enjoyed this video. See you in the next one.